Here's some images that reflect some of the things we've been talking about. First derivative, positive, and then negative. Here's a local max. First derivative negative, and then positive, local min. Notice these situations. The first derivative is positive, and then it stays positive. We have a point where the derivative is actually equal to 0. In other words, this is a critical number, but because we don't have the condition of changing sign, the derivative changing sign on either side of the critical number c, we can't say that this is a local min or a local max, and that makes sense if we look at the picture. Similar thing happening right here. Let's work out a few examples for finding local maximum and local minimum. Remember, that's when the derivative changes sign. Our first function is going to be x plus 2 sine x, and we're considering that on the interval 0 to 2 pi. We'll start by taking the derivative. So we have f prime of x is equal to 1 plus 2 cosine x. Now remember, there was a condition that we have to figure out where the derivative changes sign. And to figure that out, we need to figure out where the derivative is equal to 0. That's why we're setting the derivative equal to 0. If I solve this equation, I'm going to have cosine x equals negative 1/2. I have to think about where are the x values in 0 to 2 pi where cosine of x is equal to negative 1/2. It'll help to make a little graph of cosine. So between 0 and 2 pi, cosine looks something like this. And cosine has the value of negative 1 at pi, and positive 1 at 0 and 2 pi. Where is cosine equal to negative 1/2? Turns out that that's going to be at 2 pi over 3. That's the only place where the derivative is going to equal 0 in this interval of 0 to 2 pi. Or wait, actually that's not true. There's another place right here. That turns out to be 4 pi over 3. So now we consider our number line. We have 2 pi over 3 and 4 pi over 3. We're trying to figure out where is the derivative going to be positive and where is it going to be negative. We can choose some test points. It's always good to choose test points that are relatively easy to plug in. So what do we have? To the left of 2 pi over 3, we can pick, let's say, pi over 3. The reason I'm not picking 0 is at the very end point of our interval, and we're trying to consider places where the derivative is defined. When we have a closed interval like this that's defining our function, I can't figure out what the derivative is at each of the endpoints. It doesn't make any sense because I can't really draw a tangent line at an endpoint like this. So I have to pick something other than 0. I'm going to pick pi over 3. And then between 2 pi over 3 and 4 pi over 3, I think I'm going to pick pi. And then after 4 pi over 3, again, I can't pick x equals 2 pi. I have to pick something else. Maybe I'll pick this number. This number is 3 pi over 2. Okay, so when I plug in the test points, I think what I'll have you do is pause the video, check the test points, and then unpause the video and check if you got it right. So if you check the test points, you would have gotten that to the left of 2 pi over 3, the derivative is positive. Between 2 pi over 3 and 4 pi over 3, the derivative is negative. And to the right of 4 pi over 3, the derivative is positive. What's the conclusion that we write? Well, we say that we have a local max at x equals 2 pi over 3. And we say we have a local min. Local min, remember derivative changes from negative to positive, that's a local min at x equals 4 pi over 3. Now try this next example, pause the video, take the derivative, figure out where the derivative is equal to 0, find the places where the derivative is positive, where it's negative, and then use that to determine where there's a local minimum and a local maximum. Okay, so here's some of the work. We took the derivative, we set it equal to 0, we attempted to solve for x, and we had a kind of a weird situation here. Remember, we have to be careful with anything that has negative exponents. What we should notice at the second to last step here is that if I plug in 0 for x, I'm going to have a situation where the derivative is undefined. So y prime is undefined at x equals 0. That makes it a critical number. Remember, it's not just the numbers where the derivative equals 0, it's also where the derivative is undefined. As you can see by the algebra work, we got a place where the derivative does actually equal 0, and that's x equals negative 1. We make the number line with 0 and negative 1 on it. And then we're going to test some points. So we'll try, I don't know, x equals, let's pick negative 8, because I can take the cube root of that really easily. And then between negative 1 and 0, maybe I'll pick, I don't know, negative 1/8. And then to the right of 0, maybe I will pick 8. So try those, see what happens. Again, you should get positive, negative, positive. So it's going to be the same as the previous example. We're going to have a local max at negative 1 and a local min at 0. Remember, this local min is going to look like a corner or a cusp because that's where the derivative is undefined. So our final statement is y has a local max at x equals negative 1, and a local min at x equals 0.